Alrighty, good afternoon, everybody. Welcome back to the RSN Spring Conferences presented by WPI. I'm Francis O'Rourke. I'm going to be your host here for the rest of the day. Up now is some great guests. I'm very happy to have all you guys here. Leading them off, however, to talk to us about machine learning for FIRST Robotics is Brad Miller from WPI and WPILib and Team 190. Brad, go ahead and tell us about yourself and introduce your team.
Okay, I'm like Francis said, I'm Brad Miller. I've been doing WPILib since the C-RIO, since 2009 when we first released the software, and since then our group has grown a lot, and so there's probably about 8 or 10 people who are contributing to the software library right now, all over the place. From WPI and from the rest of the country, And with me are some members of the team who have been helping, in particular, with the machine learning stuff and with other parts of the library. So first is Frank Grossman, who's Frank. Go ahead and introduce yourself.
Hi, I'm Frank. I have been doing FIRST for about 18 years as a mentor, and I director for all the FIRST programs in New Hampshire, and also a lot of times go by chief instigator because I like to take ideas like machine learning and try to get it going and exciting people about things.
Okay, Grant.
Yeah, hi. I'm Grant Perkins. I am a student on FRC Team 190. I'm also a WPILib developer. Yeah, that's pretty much it. And I'm also going to be a student at WPI this fall.
And Austin?
Yeah, hi. I'm Austin. I'm a current WPI senior studying robotic engineering and computer science. And I got started with FIRST all the way back in 2010 and started helping out with the WPILib development stuff starting in 2016. So, yeah.
All right.
Okay.
Hey, so thank you all for joining us. Really quick, Brad, I want to ask you this now and forever, once and for all. Is it WPILib or is it WPILib?
So I've been calling it WPILib, like WPI library, since we started. But then other people have been calling it all sorts of things. Okay. So I don't really care as long as you guys are enjoying it and it's working for you and you're happy with it. Then call it whatever you want. But
all right, sounds good to me. Well, gentlemen, thank you all for joining us here today. I want to thank you all for being here, and I also want to, of course, thank some of the folks that helped make this happen, and that is WPI. WPI, or Worcester Polytechnic Institute, is a leader in project-based education for a number of years and has been the first university to come up to offer a Bachelor's of Science, a Master's, and a PhD in robotics engineering. So if you're interested in becoming a student and going to school with some of these cool people like Grant and Austin, or if you are looking to help out sponsor one of the projects that WPI runs, you can learn more information at wpi.edu. Well, with that all said and out of the way, Brad, I invite you to go ahead and start us off and tell us a little bit about machine learning for FIRST Robotics here.
Okay, great. So let's start out and I'll tell you a little bit about what we want to do today. We're going to start out with a high-level overview and kind of talk about where this fits, what we've been doing, some of the goals, and some of our partnerships that we have, and how this all goes together. I'm going to do that part of the presentation, and then Frank is going to take over, and then he's going to be talking in a little bit more detail about how machine learning works and a lot of the jargon and what the mechanisms are to make this work on your robot. And then the last thing that we're going to do, which is actually going to be really interesting, is that Austin and Grant are going to do a demo and actually show how to train a model and run inference and see all the stuff running on the computer. So not only will you be able to hear about what the stuff is about, but you'll actually see it running in a way that you could reproduce yourselves. And then, of course, we'll have questions after that. So let me get going. the current state of computer vision has evolved a lot in FRC, and I'm talking about FRC predominantly because that's what I work on, but a lot of the stuff applies to FTC, and in fact, in FTC, there's machine learning stuff also available. And we're talking about maybe merging some of the solutions, but that's sort of where it is right now. So the current state of computer vision FRC started out even with the CRIO back a long time ago, where you could run, at the time it was NI Vision on the CRIO. And then as we progressed on to the RoboRio, where it was a computer running Linux, and it was a regular, a real nice microprocessor, good Cortex microprocessor, we were able to get OpenCV ported, and so you could run something that was more traditional that you were likely to see in school as you went on to college or were doing research. And OpenCV is really like the largest computer vision library platform probably that exists, and that's what most people are using. And that ran okay on the RoboRio, but it started bogging down as people are doing more and more complicated things, and as more and more stuff is happening on the robot. So people started putting coprocessors on connecting them to the robot network, like a Raspberry Pi, and that worked out really well because there's a complete network on the robot, as you know, right? There's Ethernet. You could plug a Raspberry Pi into the second port on your access point on the robot, or you can put a switch on the robot and plug in other devices. And so the Raspberry Pi would then start doing would start offloading the CRIO, or I'm sorry, the RoboRio, from having to do the very compute intensive vision process. And that worked out pretty well also. And it's a really, really nice solution. And in fact, the WPILib team there's a talk about it just yesterday.
Actually, if you want to learn more about this, up on YouTube, we have a video where Peter Johnson talks about this for a good hour and shows a live demo on how to get a Raspberry Pi working on your robot.
Yeah, so we did everything we could do to simplify the process of connecting a coprocessor like a Raspberry Pi. That's when we standardized onto your robot network. And we even have, you can just download an image of bootable image of the stuff that needs to run on it. And then you can run your vision code on the Raspberry Pi, and you can use network tables to connect and communicate between them. That worked out really well. Some teams wanted to have more performance and do more complicated, vision examples. And so some teams were actually just getting the NVIDIA Jetson, and NVIDIA was offering some really good deals for first teams to be able to pick up the hardware and put it onto their robots. And then they can run OpenCV or other computer vision algorithms right on the Jetson at much higher speeds, higher frame rates, maybe do better recognition, and have better algorithms. But this stuff the Jetson is getting to be a little, it's getting to be kind of complicated to put onto the robot and program and all that stuff. And so the solution that we were supporting was the Raspberry Pi. So the idea is that with all this stuff, the whole idea is to be able to recognize objects which are on the field. Maybe they're game pieces, maybe they're field elements, and you want to be able to see those so your robot can interact with the field. I mean, robotics is all about first sensing and then doing some perception or computation based on the sensor data, and then driving actuators. So, for instance, if you wanted to drive to a goal or to something else or line up with the target, first was putting retroreflective tape to identify goals or identify targets or interesting places on the field, which made it really easy to recognize. And the technique that people used, of course, was just to put a ring light, ever increasing brightness ring lights around their cameras, and be able to hit the retroreflective tape. And the really cool thing about retroreflective tape is it's got the characteristic that when you shine a light on it, the light reflects back. All of the light reflects back to the source of the light that you shined on it. So if you put a ring light around the lens of your camera, it just lights up with the color of the ring light. And if you turn down the sensitivity of the camera, then all you see is the target. And so one of the things that we started doing about 5 years ago, was to start going out and taking pictures on the field before kickoff of targets from all sorts of different angles and distances and directions and all that kind of stuff, so that you guys on kickoff on that Saturday or Saturday right after kickoff ends at noon, you just download all these images and you go to town starting to write your vision code, and this gets you like 90% of the way there for being able to do recognition of stuff on the field. And you can get programmers going on that without having to build field elements. You don't need robots. You don't need anything. You just need a computer with this set of images, and then you can start writing your computer vision code. So that worked really well. But as we were looking at this, and especially as FIRST was looking at it, there's one thing that's really obvious, that in the real world, people don't put retroreflective tape around everything. So, I mean, it's like, it's just not, it doesn't exist. I keep saying that. I say, oh, people don't put retroreflective tape around all this. And then I'm thinking, like, I have a car that has a camera on it and can kind of look at stuff in front of it. And highway signs are retroreflective and lane lines are retroreflective. So really the world is following FIRST's example and putting retroreflective tape on everything.
Wait, Brad, you don't leave your house wearing a high-vis vest every day?
Yeah, I mean, but really, it's the problem is that, that these cues just don't exist in the real world. I mean, everything isn't bracketed with retroreflective tape. And the other problem is that we, in FIRST, in the game design, what FIRST does is they try and pick the things that they think make the most sense to highlight on the field. I mean, that was their strategy. And so they would do goals, or they would do other things that you wanted to be able to drive to, or help identify your position. And that's what they did. But very often teams would want to be able to recognize other things. So you might decide that a winning strategy is to recognize fuel or recognize things that don't have tape on them. And then you had to write kind of complicated code to be able to recognize stuff. So if you think about it, if you wanted to write an OpenCV program that recognized this, like, what do? Like, maybe you look for a circle, white circle that's on a gray carpet, maybe with some yellow stuff, and maybe it's got some black, a circle inside of it, like, who knows? But it starts getting like really, really complicated. And that's kind of where machine learning starts coming in, because having to write the algorithms to recognize every one of these kinds of objects, and they get more and more complicated, and you get more and more examples of things that would be hard to understand, write an algorithm for. Just starts making that pretty hard to do. So I'm just going to go and tell you a story. A long time ago when I was a Ute, I wrote chess programs. That was I enjoyed playing chess. I was in a chess club. I did computers, software engineering for a living. And I said, boy, it would really be cool to be able to write a chess program. And a lot of other people had done that. So a long, long time ago, before there were iPhones and laptops where you can just go and download a chess program and all that kind of stuff, there were a few programs that existed. And so I wrote one. And the thing with it is, it's like really hard. You gotta be able to look at chess positions and be able to give them a score. And, by doing all these crazy algorithms and heuristics and, like thousands and thousands of lines of code to be able to understand a chess position and kind of figure out, infer whether it's a good position or a bad position. And in fact, in 1997, IBM had a computer called Deep Blue that did exactly that. But their computer was like way faster than mine. When I first did this, my computer had 16,000 bytes on it of memory, compared to the 16 gigabytes of memory that computers have these days. So they were able to beat Garry Kasparov, who was the former world chess champion. And it was a landmark thing in artificial intelligence. But it worked the same way that my program worked. I mean, much better, but it worked the same way my program worked, where it evaluated board positions and figured out scores and and it did this, look ahead stuff. So it said, oh, at this time I can make all these moves. And if I make this move, then what will the opponent do? And if they do that, then what will I do? And it kind of went down this tree of looking ahead at moves in the future. And when it got to the bottom level, it would say, oh, what's the score of this board? And it would score all these board positions, and the scores would percolate back up, and then it would pick the move that resulted in the future in me having the best score. And that's kind of the way this stuff works. But now that's like that's old artificial intelligence. Now machine learning kind of came into the picture. So the old way of doing this is what we just talked about, where you have some algorithm, some traditional AI algorithm. You put it in a board position. You have a bunch of rules, which are all these heuristics, and this score pops out. This evaluation of the board position, and then you use that to figure out the best move. With machine learning, you put in the board positions, and with each board position, you put in the evaluation for it, the score, and then the computer learns the rules. And in fact, Google had a spinoff called DeepMind, and they did a program called AlphaZero with a bunch of fancy hardware and a bunch of really good software. And it was so good that it was able to, through using other kinds of algorithms, but machine learning stuff, they were able to just teach it the rules of the game, like how the pieces moved, but no strategy, none of those heuristics, none of that other stuff that I did or Deep Blue did. And it was able to, in 4 hours, it was able to develop a deep learning model that could beat anybody in just 4 hours from just the rules by just going through and training itself. And Frank is going to talk a lot more about how that training process works. But so the question is, I've been doing this digression about chess, and you may say, well, how can we use this? I mean, like, what does it have to do with first? And so you take a look. This is how we were doing image recognition until well, this is how we're doing it right now. This is how everybody does image recognition in first right now. You get a bunch of images, you get some very complicated algorithm with a lot of heuristics that help figure out whether or not you're looking at a target or what target you're looking at. And then it comes back and says, oh yeah, there's a target and here's its coordinates. Okay, that's nice. But if you take that same analogy that we did and with machine learning, you put in a bunch of images. The images are labeled. What that means is that all the interesting spots on the image have boxes drawn around them. And for each box, you annotate the image with what the thing is, what the class of the thing that you've drawn the box around. So you may have balls, you may have all kinds of other stuff, field targets, things like that. You draw boxes around them, you say what they are, and you put all this stuff, hundreds or thousands of images into this machine learning algorithm, and rules pop out. This trained network pops out, and from that, you can then determine what the thing, what's going on. So here's like an example. I mean, this is a car that's just recognizing all of this stuff. So this is a model that was trained that has people, and it's got cars, and it's got traffic lights, and you can see that as it's driving, it's just recognizing all of the stuff that's in the scene. And this is like what Tesla does and what everybody else does for their self-driving car. And so what we want to be able to do is apply this stuff to first and make this stuff available for all the first team. So machine learning is all about algorithms that let computers learn from data, and then it makes decisions based on that data. And the idea is that teams can potentially identify any objects on the field, not just the ones with the retroreflective tape. So that means that you guys can decide what the interesting objects are that will help you have a winning strategy. And it's not necessarily up to first or whoever, the game design committee who's putting tape on things, but you decide. And so the learning is based on this high quality training data, because like we said, we put all these labeled images in. This training process happens, and then you get this algorithm that pops out or this trained model that pops out that then you can use to identify things in images yourself while the robot's driving. And one of the nice things about this is that if you take pictures in lots of different kinds of lighting conditions, that makes the solution very tolerant of different ambient lighting. So all that camera test stuff that you do on the field, you don't really do as much of that because you've already trained it for lots of different kinds of lighting. It just kind of works. It's very tolerant to those kinds of changes. And so this is like a much more real world solution. This is much more like what's going on in the world. This is now modern artificial intelligence. So our goals in doing this project are to give first students a really good glimpse of what's going on, a really good, at least a little bit of an understanding, and then they can go deeper and deeper as they want. A good set of skills about what's going on in the world with artificial intelligence. And artificial intelligence is like all the rage right now. Machine learning is all the rage. I mean, everywhere you go, you're seeing all sorts of applications that are using this. It's really good to have some experience with it. I mean, people are using there's machine learning, like vision algorithms that are looking at MRI images and detecting cancer. They're doing all sorts of stuff, crazy things. You've probably seen examples that have been online where people think they're talking to customer service agents, on the phone, but they're really talking to a computer that's using that's used machine learning. You can understand what they're saying. You can give answers. I mean, it's pretty crazy. And so the idea is to give everybody kind of a taste of how this stuff can be used for doing vision and recognition. And it really enhances the gameplay, it makes your autonomous and teleop stuff better. We can even put up cues on the field if we wanted, like signs with words and with picture, like stop signs and arrows, and that the computers can recognize, that also people can recognize, people in the audience can recognize. So you can put up all these cues and stuff versus retroreflective tape. People can easily, you can put up something and label it and say what it is, and then the computer can recognize it. And so the teams get to create a really good solution. All of you guys get to create your own solutions. It's really good. And the other goal that we have for this that's really important is we want this to be something that that you guys can figure out. I mean, you understand about the kind of soft 6-week build season. We understand that this is something where you gotta get going and you have to build the robot. So the whole idea is to provide a solution that kind of is very easily understandable when you get started, but there's a lot of headroom in the range of solutions that you can implement. So, and you'll see that in a second. The idea is that you can, and we call that gentle reveal. I mean, the idea that we start out showing you something that's very easy to implement, like we'll give you a lot of help, and then you can go more and more in depth and learn more and more about to make your solution be that much better, and maybe make it that much more robust. The other goal we have is that machine learning, as you've probably heard, is very, very CPU intensive. There's a lot, you need expensive hardware to do training often. And so some teams, there's a big range of hardware that teams have, computers that they might do this on. Some teams are, people have these gaming PCs with like really expensive GPUs and really fancy, resources. It would be great for running machine learning, but other teams don't. And we wanted this to be level for everybody. And so the idea was to figure out a way that everybody would have the same access to these algorithms and the ability to do this. And you'll see how that works in a minute. And eventually we wanted to make this work with FRC and FTC. So one of the things that we did was we thought it'd be real important to partner with industry to have a really good solution. So we're working with Amazon and AWS, Amazon Web Services, and with Google, and for both compute resources and for the Google Coral Compute Stick, which we'll talk more about, and the WPILib team, and then another company called Supervisely, and you'll see more about what they do. So these pieces are, Supervisely is a website where you can upload all the images that you have. And in fact, we do that. We upload all these images that we shoot at the beginning of the year before kickoff. And we make those available, so you can in Supervisely, you can then go and use the labels that we provided. So what we did last year, it was sort of a test run. We kind of labeled all of the images with some of the field objects. we put them up unsupervisedly. But the idea is that you can put your own pictures up there or use our pictures, and you can label them. Then we have Amazon and Google for providing cloud computing resources, which help make it, which give everybody access to very powerful computers to do the training. And then we have we're supporting the Raspberry Pi and the Google Core, which is a very inexpensive accelerator. It's called a tensor processing unit that lets you run TensorFlow, which is a machine learning platform, and it makes it very, very performant. So the process, what you go through to use machine learning is you first acquire images, and then label them, and then you do this training stuff, and then you do inference. And inference is what happens on your computer or on your robot, where it's recognizing things as it's running. So we'll provide this data set, which has some stuff labeled. You can then use your own. You can label more stuff. You can retrain. You can add your own image. So we're going to provide images, that look kind of like this. This is stuff which we did this past year, and you can see the labels. And this is what supervisory looks like, the user interface. So you can see that there's an example. You can draw these boxes around these images. So if you have a team with a bunch of people, or maybe even a group of teams that want to work together, you can get a bunch of pictures that you take or our pictures, and you can label stuff. So maybe that tower in the truss is an interesting thing for you, an interesting landmark, and you want to be able to find it. You could draw a box around it, and you can label all of those that appear in every image and give it a tag or a class, and then you can train your network to be able to find those. So it's a shared resource for labeling and looking at images. And then the next part is training, and this is like the key part of all this. And like we said, we want this we have a base training script, but then it gets more and more. You can enhance it and do more and more stuff with it, and we want to have these cloud computing resources so you guys could, so everybody could do it. So even if what you have is a classmate computer, the kit of parts computer, you can still do this because you're just running it online. Running the training online. And then the last thing for inference, like I said, is this Google Coral. So here's a Raspberry Pi connected to the Google Coral compute stick. It's just a USB device. And then there's a camera there, and you just use it. And then the user interface on the left, if you haven't seen, is the FRC vision stuff that Peter Johnson did. And with this, you can just upload your machine learning stuff to the Raspberry Pi, and then use it with network tables connected to your robot. So this is sort of a summary of what's going on. It's kind of an introduction to what we're doing. And now,
actually,
I'm gonna
real
turn
quick,
it over to.
Real quick, Brett, I just want to ask you a quick question. So we saw the images there of this year's game and the field and stuff, and you said those are available right now for teams to use if they want to get working on this whenever. Is the intent in the future that you would provide similar images for the 2021 game so that teams could start this like on kickoff day?
Yeah, absolutely. This is something that I started doing with First a long time ago. It just seemed like it was really good if teams could get going right away on kickoff day. You don't have to wait till you build field elements or you put up tape. You don't have to worry about your environment not looking like the official field and all that other stuff. So we just went out on the real field, during the kickoff video filming, which is like a month before kickoff. And we went through and took a bunch of images of stuff that we thought was important. And then we post those on kickoff day so that everybody can just start right then. And you don't have to build things. You don't have to worry about, lighting or differences in field construction, right? And our intent is to continue doing that.
So as part of that, do you guys already sort of locate objects, do the identification portion of it, or is that left up to the teams to do as they need to?
Well, what we did this past year was we identified yellow ball and basically nothing else.
Okay.
And then we left it to teams if they wanted to go through our images and then label others. And it will probably continue to be that way because we'd like to be able to let teams that don't have a lot of experience or time or whatever to be able to get going right away with this stuff. And so what our hope is to be able to give you something that's pretty close to a solution that you can integrate into your robot program pretty quick. But then as you either get more and more experience with your team, or you want to make your program better and better, you can label your own ENR images, or you can go take your own images.
Cool. And so last quick question on this. How well does this work through water, for example? Let's say hypothetically we had a water game next year.
Oh, yeah. Well, that's an important consideration.
Yes,
and,
certainly.
Because there's a lot of refraction and things which happen, between
Yes.
air and water, and but when you train the model, it will understand that stuff, and it should work just fine.
All right. Well, you heard it here first, guys. Guaranteed underwater working. Anyway, sorry.
Okay.
Go ahead. Continue, Brad. I apologize. It's some good questions there.
Thanks for asking the questions.
No problem.
So I'm actually done. I'm going to turn this over to Frank now, who's going to give you a little bit more in-depth talk about what machine learning is and all the jargon. So here we go.
All right, I'll try to give you a quick fire hose of a whole bunch of machine learning stuff and fill your heads quickly so we can get to a demo and see what it actually looks like. There's a lot of times people interchange machine learning and AI, and it turns out there's no real consistent definition between the two. So the one I'm going to use here for this presentation is, machine learning. We're doing, which is object detection. So we train the machine to detect the objects, but we're not asking it to make any decisions based on the identification of those objects. Where artificial intelligence might be that eventually your robot will see a portal, a power cell, and say, I want to go get that, and not hit any robots along the way and figure out the most efficient way to do that. That would be more artificial intelligence. So this is a good view of a very simple neural network, but let's just talk a little bit about it. There's an input layer and an output layer, and then all these hidden layers. And the ones we're working with are a bit bigger, because if you think of the input layer, we're inputting all our pixels. So if you're using a small 640 by 480 image, you've got all those pixels times 3, because you've got the red, green, blue. So quite a few input layer nodes on your layer. And then the output layer is going to give you information about what you went through the network. And the network is sort of used in two different ways. And first, it's used in training. And so if you think of those input coming in, a pixel coming in, it goes to hidden layer 1, the first pixel going to the first one, but also giving its information to all the other nodes. And what it's trying to do when it's training is create weights. It uses an algorithm for each one of those nodes, and it creates what's called a weight for each one of those circles. And it keeps on going all the way through the network. And so when you then go and use inference, when you're just looking and trying to get to detect the object, it will send the weight, the pixels through, and then based on the weights that it calculated originally will sort of be how it ends up getting the data in that output layer. And it's actually some pretty interesting algorithms, and there's a lot of different type of algorithms being tried and used these days to get these networks to work in different ways. And it's pretty interesting math to look at. One of the reasons that we'll talk about GPUs every once in a while is that a lot of the math, for those who've either done matrix math or linear algebra, it's based on a lot of matrix, and it turns out that graphics, especially when you're doing video games and things are moving all around and rotating and everything else, that's all done with matrices. And so GPUs are extremely good at that, which is why we end up using a lot of GPU time when we're training.
And really quick, just to punch in here, if you want more information on that sort of diagram that we guys showed and how that works, there's a really, really great and very approachable video on YouTube by the YouTuber 3 Blue 1 Brown that I'm going to put in the chat that goes into the the intricacies of this particular status works. If you want to learn more. So anyway, thanks. Go ahead and continue, Frank.
Yeah, very cool. So a couple types of machine learning. One is unsupervised. That means that there's just a ton of data, and the machine learning is trying to cleave and move that data into areas that sort of seem to clump together, and then trying to make decisions based on that happening. A really interesting company that does unsupervised learning is a company up in Canada called Blue Dot. And what they're very concerned about is medical information and how medical and people move around. And it turns out on December 31st of last year, they had an alert go off that says, hey, in this section of China, there's actually a whole bunch of pneumonia cases happening that's really unusual. And what's going on there, we're not sure, but if it happens to be a disease, here's the flights that are leaving in China, and where they're going and where this would spread. And it actually was a very accurate early model of what was happening with the COVID-19. As it got more complicated and spread more, it wasn't the right model for that, but it was very early detection. So pretty cool what unsupervised learning can do. Supervised learning is when we're tagging the data, as we're talking about labeling data here. So object detection is a really good use of object detection and supervised learning. So I'm going to go through the parts here of the process, the data set, and then the training, and then the inference, just to give you a roadmap of where we're going to be going. So I'll give you the idea of that. And I'll start with the data sets. And a lot of people are starting to hear the term software 2.0, and that's because companies are starting to spend more time with their data sets than they are with the program. So if you look at something like Tesla, they are collecting just thousands and thousands of pictures every day from their fleet of cars that's out there, and they have to label that information and prepare it. So they're actually spending more time with that data than they do with the actual programming around it. And we've talked a little bit about what labeling is. Labeling can be done in a couple different ways. We talked about putting boxes, bounding boxes around items. You can also do something called segmentation, where you actually, if you think about Photoshop and its magic wand, when you want to like cut out something, it actually goes right around the object. So you're only looking at the object. And an advantage of that is if you think about like that side of that car, if we had accurately done that side of the car and we knew the dimensions of it, I can actually know then from the angles and everything else where I am XYZ compared to the side of that car. Really cool in the real world, and also could be pretty cool in a field, like if there were a bunch of objects around a FRC field that had good segmentation on it, you might know where your robot is at all times, which could be pretty cool. When you break up a data set, you actually train you label the whole data set, but you can split it into training and evaluation sets. And for our examples, we're actually letting the system automatically do that because almost every picture has some power cells in it. But if you're thinking about like Google, they want to make sure that a stop sign with a sticker on it is in both the training set and the evaluation set. So they have to be very careful about how they curate their data. And ground truth is just a terminology used for the labeled data. That is your ground truth, and then anything the system does is a predicted piece. So you always go back to your ground truth to know what the truth is. And if you think about these two pictures, right? If Tesla had labeled all of the cars and labeled all the bicycles, but suddenly you get this next picture. You might be speeding along and suddenly your car halts because it thinks bikes are crossing the road. Really bad thing for your car to be doing when you're heading down the highway. So you could see the problem that you got to be very, very careful in labeling your data. And they actually decided to label this as the whole thing being a vehicle, but had to make a decision on that. But again, the cool thing is, pretty bad bug in your software that you might slam on the brakes on a highway, but you can be fixing that through the data. You don't have to go back and reprogram an algorithm to be changing that, because once the network is trained on that, it'll now accurately give you back the correct information. Again, we talked about using supervisedly, and we'll do that. It's nice in the cloud. But I do want to encourage sort of this gentle reveal type of thing. The first time you might just straight use our data. And as Brad said, we go in and label a bunch of that data. We don't label it all because, you know, we want people to still do things. So we want people to go in and enhance our labeling set, and maybe halfway through the season, when you have a bunch of camera data off of your own robot, you might create your own data set. So, in fact, you know, teams could, I can imagine a future where, you know, every team puts in a couple hundred pictures, and we all label it, and now we have, you know, 500,000 pictures or something, which would be really cool to train on. So these are, we're going to jump into training now, and these are a bunch of the steps in training, and I'm going to go through them a little bit one by one, just to get into a little further depth to explain what all these are. And the first being Amazon Web Services. Amazon's a pretty interesting company. Early on, they saw that they needed a data center to do all the processing they were doing with their website. And so they created a couple of data centers across the US, each one about the size of a football field. And as you can see, all those lights on there, those are each CPU units. And they said, you know what, let's make a business out of this instead of just using it ourselves. And this is over $1 billion business for Amazon. And so they created all these, and that you can actually just go in and use services. So you can go in and say, I need a CPU with about 10 computing units, whatever that is, and this much memory, and it'll spin it up. And then you can say, I need an operating system. Let's use Linux. I need a database. So it's really nice because you can just sort of grab all these things or load all these things into these services. And they provide a whole bunch of their own services, and including one that's pretty cool, which is balancing. So if you think about Netflix, which actually runs on AWS services, so Netflix doesn't own any of its own servers; they're actually all renting them. And but if you think about watching movies, you know, at 2 a.m. on a Tuesday, there's probably not as much movie watching going on as a Friday at 8 p.m. And they don't want to be spending money for all those CPUs as they would at their maximum at 8 p.m. on a Friday, when there's a whole big difference. So there's this automatic balancing that happens that Netflix doesn't have to go in and manage, but that Amazon Web Services manages, that automatically takes them down to the right size for what's going on at the time, and actually automatically spins up new servers when needed. So it's a pretty powerful paradigm. And also, as Brad said, it means that we can do some pretty intense training of our networks and not have to depend on what kind of computer you have, but more that you have a network connection to get to some web pages and do that. So it's a really nice way of going about it. SageMaker is one of their services that we'll be seeing. That's a service that knows about machine learning. So it takes these things I'm going to talk about in a moment, which are Jupyter notebooks, automatically spins up instances as you need it, and passes all the data and the data sets to them, and comes back with the trained data at the end, or the trained network at the end. So it's a pretty cool service that we'll be talking about.
And real quick, can I just, I heard a stat recently that AWS powers like some huge proportion of just the internet in general. Is that accurate?
Yeah. There's a lot of programs or companies that run their services on there, because they have all the platforms you need. So you can run Windows, you can run Linux, you can run any kind of platform. And so I don't know what the percentages are, but I know that companies, almost every company I talk to ends up on Amazon.
Wow.
So what's TensorFlow? This is an open source machine learning platform, actually can be AI platform as well, and that is maintained by Google and started by Google, but it's open source. And it uses as a mathematical model between those nodes as a tensor. And if you've studied tensors in mathematics at all, they're pretty powerful. In this case, it's really a vector with a an index on the end of it. So if you think of each of those lines going off and to the right, that's the vector, and the index being the weight that it gets assigned to it. And that's really powerful to do in a mathematical model. And the way that TensorFlow works is you work in a language, usually Python, and you describe this whole network as a graph. So you tell it how many nodes it's going to have in each layer and everything else, and then you tell it the mathematical models that you want to apply to each one of those nodes, and then it produces that whole neural net for you, and then you can pass data into it and start training. So it's a pretty nice resource for building these networks. And there's other ones that I mentioned here, PyTorch and Keras, that are also good platforms. We went with Google and TensorFlow because we were working with Google, and also because they had a TensorFlow processing unit that helps us on the inference side. Transfer learning. So what we're doing here is we could start and design one of those neural networks and then train it for what we want it to look for and get the data out. But it turns out that a network needs a little bit more information to start with. So you're putting in all these pixels, and it sees it a bunch of pixels, so it doesn't even know there's objects within these pixels, and you have to train it that there's objects before you can just detect a specific object. And the example I give is if any of you have traveled or gone into a foreign language class and had someone speaking a different language, when you first hear it, it just sounds like one long string of noises, and it's hard to pick out the words because you don't hear the spaces in between the words. As you get to know more about it, you start to hear those spaces, you're able to pull out the words, and you're able to start understanding the language. And it's very similar to that, and these networks need to be trained in that way first. So it turns out there's these really large data sets out on the internet that are fully labeled. One's called COCO, another one's called ImageNet. The one we use is COCO. And that data set has everything that you can imagine labeled in every picture. And the network then is trained on that and then gets saved out at a point where that's fully trained for all of those objects. And there's these things called model zoos out there where you can actually go and look through them. We actually use one called MobileNet. And you pick your model a little bit based on your inference requirements. So as Brad talked about AlphaGo that was trained by Google in 4 hours, they needed a lot of resources both for the training and for the inference of playing that game. But we don't have that on our robots, so we pick a model that's more designed for smaller devices. And MobileNet runs nicely on like an Android device, powerful Android device, or on the Raspberry Pi and Coral that we're talking about. So there's these nice models out here that are already trained. You can go in and see the graph of how complicated those networks are, but for the most part, we're saying it's a good place to start. And what we'll do is just train the end of that network, the last few layers, and tell it exactly what objects we're looking for. So it sort of says, okay, I came through here and I found all these objects. Which ones are you interested in? And now we're training it for which ones we're interested in. So that's the idea of transfer learning, and saves us a lot of time in training. When we're doing the training and we use Amazon SageMaker, they use something called Jupyter Notebooks. And Jupyter Notebooks is a concept and program that's out there in the wild, but they're really nice. And you can sort of see there at the top, there's documentation going on, and then there's that gray area. And that gray area is a snippet of code. And you can actually have intermix of documentations and snippets of code, and you can actually just run one snippet of code, get some output, go in and maybe take some of the output, edit the next snippet of code, put it in there, and run that. So it's a really nice way of getting this documentation and education at the same time. And the notebooks give us a really nice ability to do what we call the gentle reveal. So the first time you go in, it might be read the documentation, hit play, and you get a trained model out, right? And then the next time it might be, well, I want to enhance my data set and tune these things called hyperparameters I'll talk about in a minute. And then you might even want to go more advanced and create your own model. And WPI is actually has some seniors that are working on a tool to help out with creating models in this environment. So there's sort of this idea that you can learn more and more and go deeper and deeper as you go. Hyperparameters is, it turns out that we have all this data and we feed it in and we can do the network, train the network, but there's also a bunch of parameters outside of that that we can do to help modify how that training session goes. And I named a few here. One is epochs or epochs, which is the number of times you're going to go through your full data set in a training. And you say, well, isn't once good enough? And I always say, like, if you have a younger sibling or something, you'd be surprised how many times, you had to say, no, that's a ball. No, that's yellow to them before they got it. So there's a lot of times you need to go through the data to get the network to learn it. Batch size is how many to do at a time. Really, that affects like how much memory you need during your training. Because we do larger batches, you usually get a little bit better trained network, but it also takes a ton more memory to do that. And then, as I talked about, your training sets and evaluation sets, you can hand it specifically those sets, or you can ask the system to do it for you. I think we use about a 70-30 setup where 70% of our data is training and 30% is used for evaluation. It does an evaluation after the end of each epoch, so it's actually pretty cool. And Amazon has this cool thing called hyperparameter tuning. So there's usually up to about 100 hyperparameters, and you can actually say, these couple, these three here are really important to me. So let's go through and spin up 200 servers, and you try a whole bunch of different values of these parameters and tell me what works best. And now we know how to tune that actually network to the very, very best. And we don't allow that on our servers because even under AWS, that'll cost you quite a few $1,000s. But it's obviously, if you're a company playing with an AI, it's pretty important. And lastly, a little bit about accuracy of object detection. If you're evaluating, let's say, handwriting detection, you can easily say, there was an E, and 80% of the time I recognize that as an E. And that's pretty easy to do. But when you're doing objects, it's actually, we give you a percentage of accuracy at the end of each training, so you can see how well it's trained. And one of the reasons you want to see that is, again, mathematically, there's this, you're trying to get to the peak of your knowledge of finding those, let's say, power cells, but there's different things that can happen along the way. You can correct on your data, so it recognizes power cells only in your data set, but not in the wild. You can underdo it so that you think a lot of time you're going up that curve and there's a little bump in it and it looks like it's the peak, but it's not really. You need to come up and keep going. So by giving out those accuracies along the way helps quite a bit. And so that accuracy calculation, if you look up mean average precision, is pretty cool little calculation, but it takes the number of predictions that you got right. So let's say that you go through a training set and it says, I found 10 things on this page and 8 of them were correct according to the truth, ground truth of your data. And so that sounds like 80%. But then you go to the recall, which is, I saw 10 objects, but only 3 of those were actually correct objects. So it's a little bit different number of correct objects you got. How many of those were true positives? And so you take that calculation, and then the other is that it's always going to give you a bounding box for that object, and how well does that bounding box match up? So again, here in the green is the ground truth, the red is the predicted one. That's pretty good, but with our algorithm, I think we allow up to a 50% overlap. But after that, we consider it no longer a good match. Some of the stronger algorithms use about has to be about a 70% match, and gets pretty tough. But So pretty cool algorithms when we give you out that accuracy, sort of what it's doing behind the scenes to get that accuracy calculation. And I think after this we can go into inference. So on inference is now I've got a trained model. I've gone through all this training, and now I'm feeding my images, which are just frames from a video from your camera, into the network. And each time it goes into the network, it will evaluate that image and give you a list out of the type of objects it saw, its confidence that it was really that object, and the bounding box. And so it's doing this for each frame. And we're actually, in our case, putting that information, which is an array, into the network tables for your then to evaluate on your RoboRio program and deciding what you want to do with that. And using the tensor processing unit. So again, since it's TensorFlow and it's using tensor math, they have a compiler down that optimizes for this specific tensor processing unit, which if you're into hardware is an ASIC, and allows you to go a lot faster. So if you just ran this on a Raspberry Pi without a coprocessor there, you get 2 or 3 frames per second. I think with the Coral, we're getting over 15 frames per second, sometimes better with that. So again, the Pi Vision setup is tied in with this and has a program to work with to put all that information in the network table. So it's a pretty clean solution with no internet connection and providing pretty good view of these objects.
Okay. Yeah. So the next thing we want to do is this workflow demo. We're going to show you how this stuff actually works, and you can see it running on a computer. And for that, Austin and Grant are going to take over, and we'll share their screen, and then you can kind of see what how you do this.
Yeah, I'm really looking forward to this. So, Austin and Grant, we're going to get you guys together right away here. And while we're waiting, Brad, would you mind just to have your screen stop sharing, just so we don't end up doubling up here by accident?
Sure.
Alrighty. Okay.
Did it stop?
Not yet, but this is okay. We will.
Oh, here we go.
No, we're good. Don't worry about it. I got it. Figured it out.
I got it.
Yep. Okay, cool. All right. So, with that said, Austin and Grant, you guys can go ahead and take it away. We're going to put you full screen so everybody can see all the details that you guys have in your setup here.
Yeah, definitely. So just as Brad and Frank explained, we're going to get started by kind of going through the workflow. So showing how to label images, then training a model, and finally doing some inference to actually detect power cells. So the first thing we're going to do is we're going to hop into the supervisedly web tool and take a look at the WPILib dataset. So that's the dataset that the WPILib team captured at the pre-kickoff filming. So Grant's going to pull that up right now. And just kind of explain how the interface works. In the middle, once it loads, we'll see each image. And on the right-hand side, we can see the different images in the data set. So we have something like 4,000 images that we provided this year, and we can scroll through them on the right-hand side. So in this image, we've started to label the power cells in this image. So the top left one already has a box on it. And what Grant can do is by clicking the rectangle button, we can add a new label for the other power cells. Something really important, as Brad and Frank mentioned, is the quality of the labeling affects the quality of the output. So Grant's going to be very careful here and make sure the labels are just how we want them. And if they aren't right the first time, we can drag the corners to make them how we want. And then once the image is labeled, we can move on to the next image.
And so
Grant's going to go ahead and label the next one.
Yes.
Francis, go ahead.
So really quick. So in this situation, do you have to label like all 4,000 images? And is 4,000 like the average number you'd want, or too little, or like a lot, or how much work is entailed in doing all this stuff?
So to answer that question, just to tag on,
Yeah.
So we give our data set with like a couple hundred images labeled, and that gives like a medium weak model. You'll get some results, but you'll get a lot of false positives. You'll miss a lot of balls. We provide, WPILib provides like 5,000 images or something insane that we give you the option to label. And basically a good rule of thumb is the more data you have, the stronger your model will be. So of course we're going to recommend, label every image you can.
Right.
But it takes a long time to label all of it. And Team 190 has done this. We have labeled every single image in the entire WPILib dataset. However, to get a model, you don't need that.
Okay, cool.
Yeah. Thanks, Grant. So now that we've kind of shown labeling a couple images, we won't sit here all day and label all 4,000 images with on the stream, Francis.
Thank you so much. I do really appreciate that.
So what we're going to do is we're going to hop back out and we're going to download what we've labeled already and some things that we labeled earlier. So what Grant's doing right now is we're actually downloading the data set, which is the images and the boxes from Supervisely to Grant's computer. And that'll take some time. So while that's cooking, we'll go ahead and move on to the next step, which is logging into the Amazon Web Services console. Got to make sure that Grant's not a robot today.
All right, here comes the test, Grant. Are you?
Dang it!
Oh, I don't know. You might be a robot, actually.
That's machine learning.
So what we're going to do is we're using Amazon's servers to train the model. So this way, if you have a netbook or if you're an FTC team and you're on a tablet, you can still train a complicated model in a reasonable amount of time. So the first step is we're going to take the data set that we just downloaded from Supervisely and upload it to an Amazon S3 bucket so that they have access to it, so we can then take the data set and train it. Remember, Amazon Web Services, they exist somewhere. It's not just a cloud that's magical. There's a physical server running somewhere, and we need to make sure that our data set is accessible to that server. So Grant's created an S3 bucket named RSN WPILib demo Grant and is uploading the downloaded data set there. And the other key piece right now is we're making sure that the permissions are set correctly on this bucket. So when we go to train the data set, the other machine, the other physical instance that's running somewhere in Amazon's cloud can access the information.
So while he's doing this, I'll just quickly ask.
Yeah.
So I know that Frank touched on this a little bit and Brad touched on it a little bit, but normally using AWS costs credits and credits cost money. And you said that Amazon has partnered with WPI. Does that mean that they were offering some of this to people in the kit of parts?
Yeah. So Frank and Brad can talk more about that after the demo, but okay. The goal is to have this be accessible at some level for free for all teams.
Great.
To make sure that every team, you don't need to go out and buy 10 GPUs and hook them up to your nuclear generator or something in your bedroom to make this work. We really want to make sure that every team is able to experience what it's like to label 4,000 images, but also see that the model works in the end. And so yeah,
our goal is that no one should ever have to pull out a credit card to be able to do that.
Yep. Excellent.
So now what we're in the Amazon console is we're in a section called SageMaker, and we're going to be using the SageMaker interface to run our Jupyter Notebook and start the training. So what Grant's doing is creating the notebook, and the key piece here is that it has a unique name and it has the correct permissions again. So as soon as that's done, the next important step is, of course, WPILib is providing a lot of the code that makes this work. So what we need to do is we need to tell Amazon where that code is. And we do that by pointing it to the detect Coral repository on WPILib. The detect Coral repository has the script and tools needed to actually do the training.
Okay, and all that's available on the WPILib Git repository?
Yeah.
Cool.
Correct. Now, creating a Jupyter Notebook is pretty quick, but it's not instant because it has to go and allocate those resources for us. So we're going to open up a Jupyter Notebook that we made just before our presentation started here. So we don't need to. And when you open up the Jupyter Notebook, this is what it looks like. And it kind of looks like an integrated development environment like Visual Studio Code or IntelliJ, where you have the files on the left and an editor in the center. There's two main files that we're going to be working with. There's the testing file and the training file. So right now we're looking at the training file in the center. And as Frank pointed out in the slides, there's documentation at the top. And I highly encourage everyone to read that information, but we're going to skip over that right now. And we're going to jump straight into the code. And what we see in the code is this is what's actually going to get run on AWS. Oh, Grant's going to go ahead and restart it so it looks the way it should. Some key pieces of information that we see in the notebook that users can edit is that they can edit their hyperparameters there in, here, we'll give it a second to load up.
Sorry.
Well, users can edit the hyperparameters. They can edit the location of the data set, which is really important. So we just uploaded the data set to S3. We want to make sure that we're using our data set and not someone else's data set. And you can also edit the number of epochs and hundreds of other settings. So jump into every setting you can edit, but you can edit them all here.
Yeah, and just a quick question. So on that, like, how would I know how many epochs that I should be running it through? Like, do you guys have some documentation about what a general good practice is?
So I guess I can answer that. So we default the number to being 1,000. So that means 1,000 times we are going to run the code, detect the error with our current model, and based on this error value, we will then change all of the parameters within our machine learning model to decrease that error. So basically each step, each epoch, we try to lower the error as much as we can. So it's a very gradual rate. So 1,000 epochs is an appropriate amount of epochs. We're doing this on a computer that's using CPU only. So this takes about 3 hours to do with 1,000 epochs. Hopefully in future generations, we'll be doing GPU training. Currently that's not supported, and that takes about 15 minutes for the same amount of epochs.
Oh my gosh. Okay. And when you say GPU, do you mean like the integrated card on my laptop, or are we talking like a 1080 or something?
So we're talking like, I don't know if this is not a consumer card, but Amazon has Tesla V100s, which are about $10,000 GPUs like in their servers, and that's the kind of GPU you would have access to. And to do that, you would change the instance type to something more appropriate.
Okay, cool.
And there is no magic to those numbers. It turns out people are always tuning those parameters. So you start with some parameters, and then if you get the precision you want, you go with it. But otherwise, you got to keep playing with them.
Okay, great.
So Grant, why don't you go ahead and fill in our S3 bucket there in the script. So what's going on is by typing the unique name of our bucket into the script, we're telling our script where to go to find the data set.
Okay. So
And
just
then,
because we skipped the upload, I'm going to go back to our default bucket, which in the current year, it has the current year's data. But in a normal case, when we actually wait for that enormous upload, when we're not doing a demo, you would type in your own bucket here.
Awesome. And now the training job is started, as we can see by the feedback right below the estimator.fit line. Now, as mentioned previously, this can take a little bit of time, but what we can do is we can actually go and monitor the instance to see if it's actually doing something. So if we head on over to training jobs and then pick the appropriate one, which is the most recent one.
Yeah, so this one is the one we just started.
Yeah. And we can see what its status is. And just like when we were creating the notebook, it's pretty quick, but it still has to go and allocate those resources. So instead of waiting a few minutes for it to start, we can actually go and show a different training job that completed already to give an idea of what it looks like.
Wi-Fi is being a little slow as we're streaming. Sorry.
Yeah, this by the way, this reminds me very much of any cooking show you have where it's like, do all of this, then bake this for 6 hours. But I just happen to have this right here finished.
Yes, this is very much the turkey is in the oven, and we're going to be making lots of them.
Lots of finished turkeys here.
Yes, but all of this really does work. Right? We're just kind of jumping around in the process because it does take time. So what you can see here is you can see that once the training job was started, it immediately went and used lots of CPU time and lots of memory time, and it was also reading and writing to the disk quite a bit. So if this was actually running, you'd be able to see that and make sure that it's actually running and it didn't crash or anything. Now, the key piece of information here is at the bottom is the output. And the output is actually the trained model that we just trained. And what we can do is we can either download that model and take it and put it on our Raspberry Pi, which we then put on our robot. But right now, we don't have any robots. Hopefully, we'll get back to our robots soon. But instead of the robot, what we can do is we can actually test on Amazon using the training notebook.
Oh.
So what we do is if we open up the training notebook, as opposed to the testing notebook. Yes, if we open up the testing notebook, we can see a similar Jupyter Notebook format with some documentation and then code. And the key piece of information that we're going to edit here is we're going to point the model at the model that we just trained. And we're going to point the video either at the WPILib testing video like it is right now, or another video that we uploaded. So if I was just sitting at home and I had a PowerCell with me, I could take a video with my phone and upload it to S3 and use S3 to test the video, as opposed to needing a Raspberry Pi and a Coral and a camera and so on.
So when you do that sounds really cool. But when you do something like that, do you have to try to match like frame rates or resolutions to what your model was trained on, or?
No, it's programmed, so you just give it any, normal file type of a video. So you can do your ios.mov, you can do MP4, you can do AVI. It doesn't really matter. It doesn't really matter its resolution. Doesn't really matter its frame rate. It's just going to take every single frame, and it's going to label it the best it can.
Wow.
And the key thing to note about this is this will only tell you how well your model is performing, but it won't tell you how well your model is performing on the hardware. So if it works here, you still want to go ahead and test on a Raspberry Pi once you have access to that hardware again, because you might find that you're only getting 1 frame a second, and maybe that's not good enough for you. But we can talk about ways to improve that later. So Grant's uploading the test video, or did upload the test video, and now we can start the testing job. And again, this will take like 5 minutes to test. So instead of waiting for it to finish, we'll actually just go to a video that we created from the testing job. So what we can see is it's playing the video and highlighting the power cells. The percentage number is kind of giving us an idea of how confident the model is that what it's seeing is a power cell. So sometimes it's more confident, sometimes it's less confident. And in instances where it's less confident, those might be places where you want to go and add more data to your model to say, these are definitely power cells.
Wow.
To kind of give it the gentle reminder.
This is really intriguing
is.
because it's showing not just stuff in the foreground, but also all sorts of pictures in the background and way away from it. I wouldn't necessarily expected that.
Yeah, it's really good at detecting all different kinds of information, especially in different lighting conditions. So like here on this frame, we can see the lights are going crazy, and it's still able to detect a good portion of the power cell.
Just one thing of note, this is Team 190's model, my team. We decided not to label power cells that were like significantly overlapping. This was a decision that perhaps should not have been made, but it's okay. So that is like one place where a model could be strengthened over ours. So if we were to go back to places where there's like several power cells in a line, and they do overlap, you might notice that it just cuts out and they are not detected, and it really only is very confident on individual power cells. So there's a lot of different techniques you can do, is what I'm getting at for labeling. So you can see just there, both power cells were not labeled when they were overlapping. So just kind of interesting stuff like that is little tricks that you can do to get your model to be a lot more powerful and a lot more useful on the field.
So it looks like this model is doing a really good job of finding. It's doing a pretty good job of finding the cells, and it's doing an excellent job of providing no false positives in this case.
Yeah, because you definitely don't want your robot chasing after something that isn't there.
Yeah.
So that's a good point.
Or the person, or the referee in the yellow shirt next to the.
Yes.
Okay, that would be pretty funny at least. I wouldn't want to be the team that had that happen to them, but that would be funny at least.
190 does not support this message.
No. Unless
and then kind of a little bit about how you would use this. All of these boxes get output as coordinates over network tables. So teams can then take these boxes and either determine the angle to the power cell or how far away they are from the cell, or just display the information to drivers so drivers know what's happening. Yeah.
Okay, so in this case, you've done it with a recorded video, right? And so, can you give just a little bit of information about how this would kind of go down if you were using a webcam and the Coral as you discussed?
Yeah. So
go for it.
Oh, do you want?
No, it's okay. You go for it, man.
Oh, okay. So what you would do with a Coral and Raspberry Pi is you would configure the Raspberry Pi with the FRC Vision Raspberry Pi image, as Peter spoke about yesterday. And what we have is when you download the model from S3, there's a dialog box on the Raspberry Pi to then upload that model and use the USB camera connected to the Raspberry Pi to handle the inference. And all of the dependencies to do that are already loaded in the Raspberry Pi image. So you shouldn't need to go and install new packages onto the Raspberry Pi image or SSH in. You can just download it and upload it and press play, essentially.
Wow.
Anything to add, Grant?
Yeah, it pretty much it's extremely friendly. I actually wrote it, so I'd like to think it's friendly. So all you do is in Supervisely, you create different labels. So let's say last year, I spent a lot of time last year or last summer. I labeled like 3,000 cargo and hatches over the course of like a week or two. And basically you just create a label. I can actually go to Supervisely and show this, but you just create a label with the proper name that you want. So let's say you create one for cargo and one for hatches. This year we have one for power cells. And then all you have to do is just appropriately label in your data set what the object is. So then that data is carried through all the way through Amazon and onto your Pi. So that way when it detects an object, it will also tell you what kind of object that is. It'll tell you its location relative to the size of the image, and it'll give that all of that through network tables to your robot. So then you can do whatever you want with it. One example is in my basement, I brought home a WPILib demo bot. And basically what I had it do is I had it detect a cargo I had lying around, and it generated a path based on the size and location of the of the cargo to go and drive and balk the cargo. So it's following like S's and stuff. So that's like something you could do on the field. You could hit a button and it could go generate a path to pick up a game piece, and it will do that all automatically, no driver skill required.
And so, really, from a hardware perspective, right? If your robot already has a Raspberry Pi and a camera on it, all you need is the Coral and the software, and you're good to go.
Yeah.
And how do teams get their hands on one of those? I know that you guys talked about having a partnership with Google, but was it in the kit of parts? Because I didn't sort the kit of parts this year, I gotta admit, so I didn't see it. But
you can.
Yes,
I mean,
so the Coral is not in the kit of parts.
Okay.
It's available on Amazon actually for purchase, and it's not too bad. It's like a little bit more than a motor controller. Last time I looked, so it's like within all the cost limit that the rules have, at least this past year, and the other pieces are Raspberry Pi. So
right.
Those are also available, and teams know how to get those because we see them around.
Great. All right. So I think that covers up everything. Do you guys have anything else you want to show on the demo before we start taking questions from the audience?
The demo is pretty much complete here. Thanks.
All right. Cool. All right. So with that said, again, everybody who's watching, if you have questions for everybody, just send them in here. Oh, we got a little bit of a shuffle here with some people, but don't worry. I promise Frank is still there. Right now, if you're watching, you're seeing Grant's screen instead of Frank, but don't worry. Everybody's still happy.
Let me stop.
Nope. Don't do that, actually. It'll break everything. I'll fix it on my end later. But anyway, with all that said, I want to remind everybody, if you've got a question for these folks about machine learning, please send it into the chat with !Q followed by your question, and we're going to answer them live on air. All right, so first up here, we're going to take our first question. This is coming in from user Irwin1310, okay, and they're asking, can this machine learning be run on the Limelight along with their vision, or would a second Pi be needed to do the machine learning?
I am not familiar with the Limelight. I think that it is not capable of directly running our machine learning stuff without hacking into it. But I promise that the Pi solution is a very easy one, and it's relatively inexpensive. It's like a bit over $100. But no, I don't think you can directly run on a Limelight and still get the FPS that's desirable.
Okay. Oh, do you think is it because of like a compute thing, or is it are you guys like focusing on the more general solution before working with sort of these kind of branded products.
The Limelight is a prepackaged solution that let you, to provide you with a ring light that you can control from your program, and it's got and it's designed to do the retroreflective tape kind of solutions,
I see.
the OpenCV solution. And so the software that's pre-canned inside of the microprocessor that's in the Limelight is for OpenCV algorithms. I mean, in the future, they may be interested in trying to package this stuff in the Limelight the same way that we're doing it for the image that we provide. So right now we have an image where you just go to the web interface and you can upload programs into it that will do the machine learning stuff. And we've got the libraries in there, and it's all set, ready to go. And hopefully the Limelight folks will maybe want to take advantage of being able to support this stuff also.
Okay, cool. All right, so we got a couple of more questions here. So this one's coming in here. They're asking, is FIRST, I assume they mean FIRST HQ, is FIRST aware of what you're doing with machine learning? Any idea if they will make choices in game design to facilitate machine learning? Now, well, I wouldn't ask you guys to speak for the GDC.
Who can say what?
I wouldn't ask you guys to speak for the GDC, but I want to see if you guys have any perspective on this.
Yeah,
I think to quote Jamie from her presentation yesterday, everything is on the table at the start of the game design process, and that includes all of the technology, or at least I hope it includes all of our technology.
Yeah, I will say that that from the vice president of programs at FIRST, Chris Rake, all the way down, people are very excited about providing the machine learning opportunity for students on FIRST teams, to be able to learn. And we've been working with them, along with our partnership with Amazon that we had for last year, and they're really excited to see this happen. And so maybe something will happen in that regard.
Yes, no promises for sure, but it's at least a known quantity from FIRST HQ. Yeah. It's not like a secret feature. Okay, great.
No.
All right, cool. So a few more questions coming in here. We've got this one from Mr. R Squared. Mr. R Squared, he asks, is there a place where we could find the list of dependencies for implementing the Coral in case we want to use a different image? I have no idea what that means, but I trust you guys have a better idea.
I guess I can answer that.
Yeah.
So the GitHub, the Detect Coral GitHub, it includes the scripts we saw that are running on Amazon, and it also includes the scripts that run on the Pi. And it's just normal Python, and you can actually see the names of the different packages. I don't think there's any formal documentation on the exact dependencies that would need to be installed to run on a device other than a Pi and a Coral, because I just never thought of doing that yet. But by just examining the script, all the imports are at the top. So if you wanted to install your stuff, you could just look up each package and figure out how to install it from there.
Grant, I would believe in our zip file there are a couple versions of the model. One is a specially compiled one for the Coral, but there is also the uncompiled one, which could be used with other devices to interpret it.
Yeah. Just to add on to that, basically we have provided a model that is specially optimized to run a little bit faster on the Coral and on the Pi. So that, and then we also have one that just can run on most anything.
Okay, cool. All right, so Mr. R Squared has another question here, and he asks, is there a machine learning tutorial on WPILib or lib? I assume that means, is there like a tutorial or some other documentation on the WPILib documentation site that people can go to reference?
So let me just say something about the status of things and kind of where we are and what's going on.
Yeah.
And I'll try to answer that. So a lot of you guys may have noticed we put this stuff up. We announced it last year at the beginning of the shortly after kickoff that all this stuff existed, and there was documentation that was part of the docs at WPILib.org website that you could get to. So all the read the docs documentation includes a section on machine learning. and then partway through, there were some issues with Amazon with using SageMaker for these Amazon Educate accounts, which are what we were provisioning for team, and it stopped working. I mean, they just had some stuff, and so we ended up taking down the documentation, and we started working on another solution so that we could get around the Amazon Educate restriction, and so we have some stuff now. And we were kind of hoping that maybe for this, for this webcast, we'd be able to put it and let you guys play with it, but we're not quite ready. So I think we're kind of hoping that soon we'll have this kind of new solution, which is available if you want to play with it for free and use some of the credits which Amazon has given. So that's kind of the short answer. So we'll get some documentation up pretty soon, and we'll post something in Chief Delphi, or maybe first we'll announce something when it's back in business, and we'll let you know. So that's sort of where we are right now. We're kind of like in this period in between, having the thing go down and getting it back up again.
Okay, cool. Just a couple more questions. If you got any more left, make sure you send them in the chat with !Q so we don't miss them. This question comes in from Azathoth here, and they're asking, there's been a lot of research projects into modifications and mimicry that can throw off of machine learning. As this technology becomes more popular in FRC, do you think that the rule set will have to be updated to avoid either team-based sabotage or just team-based confusion, right? Well, I think even more generally, right, there are robots, like imagine like, Team 175 Buzz, right? They like to put a big yellow circle on the side of their robot with a smiley face in the middle of it. What are your all perspectives on that? Or do you think that the machine learning solution is robust enough to defeat a lot of the other things on the field?
My perspective is if you have a power cell in your robot, we will see the power cell, and depending on how you're coded, it may or may not chase after that power cell. You can accomplish you could label that the power cell is inside a robot, and that is how you could counter that, right? So that kind of stuff is how you could counter, chasing after a robot that already has a power cell. In terms of what I think what this question is directed about, which is like adversarial neural networks, or they have the special blurry pictures that trick a neural net into performing differently. I think that is kind of unreasonable for a first game, because you kind of need maybe a lower resolution camera than maybe you'd use for other vision solutions, because machine learning on the low level is just a ton of matrix multiplications and additions and just operations in general. So if you have like a high resolution camera, it starts slowing down. So I think it would be very difficult to do what this question is talking about, which is like tricking neural nets by wearing weird clothing. However, having a power cell on your robot or a big, yellow smiley face, I think possibly could deceive.
All right. Well, challenge accepted.
I have a yellow backpack. That's like circle shaped. And when we were testing the model back in like January, my yellow backpack would always be detected as a power cell. So you don't need to.
That was early on also though, and we did put in a bunch of yellow things that were not power cells in order to try to train it to not do that. And I think also the rule that is written currently that was put in, I think after computer vision, was forward-lookingly written to say not to be specific, but to say you can't add things to your robot to confuse another robot or something like that. So
right. Yes.
I think the rule's pretty general.
Yeah. Well, that's true. Yes. But, and not to get too deep into the weeds on this, right? But I can think of, a lot of things that people wouldn't put on to confuse robots at all, but just are part of like, the whatever it looks like that may cause confusion. But you could also defeat that, I suppose, by having whatever target you're trying to search be something more unique and challenging, right? Something more like Brad was talking at the beginning, like, or how things do in FTC, where there's a picture or some words or something that's not just a yellow orb. Yeah. So, okay, cool. All right. Well, with that said, here we go. We got another question here. This is from Azatoth as well. This is a really interesting one, actually. He's asking, what do you think of using machine learning to detect robot bumpers? Have you guys ever tried finding other objects besides game objects like that?
So the original network that this was distantly based off of, I think our training data for last year was supplemented by this team. So I believe, I forget the team number, but the RoboPanthers, they made a neural net. I think it was a YOLO V3 is what it was called. And they labeled a lot of game objects other than game pieces. They labeled lines on the floor, they labeled the rocket, and they also labeled other teams' robots. So they would actually be detecting a red robot and a blue robot. So I think it's pretty doable.
Okay, interesting. All right.
Yeah, I mean,
go ahead, Brad.
As teams want to do more and more advanced algorithms, and being able to detect other robots starts being interesting. I'm talking to you guys, Team 9100. I mean, Team 900. I mean, this is your opportunity to make a fully autonomous robot.
Yeah.
By being able to see the other robots on the field and avoid them.
Yeah, there, go do it, guys. Come on, let's do it. All right, we got one last quick question here before we end. This comes in from the chat here. They're asking, what's that wonderful creature behind both Francis and Grant? I think that's that thing over there, isn't it? Yeah. Grant, do you happen to know what that is?
Yeah, I think I might know what that is. So that is Team 190's mascot from this year. His name is Beef. He is a duck goat.
Okay.
So this year our Team 190's robot was named Duck Goat because it looked like a duck, and our robot's always named after a goat, and we wanted to play on words off of like Duck Goose. So we named it Duck Goat, and then we had to draw a Duck Goat. So that is the wonderful creature that I drew, and now it's on the back of all of our shirts.
Excellent. Well, that's just a warning to everybody out there that if you make a drawing and you think it's going to be a joke, be careful because it might actually become reality someday. So, but thank you for your artistry, though, Grant. We appreciate it.
Oh, of course.
All right. Well, and also a big thank you to everybody here, to you, Austin, Brad, Frank, and Grant. Thank you so much for joining us here this evening to talk about machine learning. I'm truly excited to see where this goes in the future because one thing that we want to try to do with FIRST, I think, is to push the boundary, right? Many of the robots are just remote controlled cars. The next step up is that plus dead reckoning. But going into something like machine learning, I think is a great thing that actually sort of gives direct application that a lot of students can use if they pursue programming in their futures. So thank you all so much for your hard work on this, and thank you for presenting today.
Yeah, thank you.
Thanks,
you.
Francis.
Yeah. All right.
Thank you, Francis.
Yeah. And with all that said, coming up in just a few minutes, we've got our final presentation for today here, Friday. It's going to be Drivetrains 201, a little bit more than 101. Gear ratio and motor optimization. That's going to be presented by Sean Lavery. We'll be here with that at 6 o'clock in just a few minutes. So make sure you guys stay tuned for that. You don't want to miss it. But until then, again, thank you to all you for presenting today, and we'll see everybody in just a few minutes.
We can do motion capture. We have